Welcome to this presentation on the weighted residual formulations. This one we'll be looking at the subdomain method. So again, going back, reviewing where we're at here, we've looked at the direct formulation and the minimum total potential energy formulation. We did the introduction to the weighted residual method in the first couple steps, and we did the collocation method on a previous video, so now we're going to be looking at the subdomain method. So again, looking back at our example, what we're interested in seeing is here we have this beam and bending. It's giving us probably a smiley face of some sort, and we have some boundary conditions we involved in this problem and the governing differential equation. All right, so we've done a lot of this stuff already, so what we're doing in this specific video is we're going to be forcing the residual error to 0 at various points or intervals, using the different methods. So that's where we're at here, and we took the governing differential equation, which I talked about or just mentioned on the earlier slide, but again, look at this development in the initial introductory video. But we have basically our governing differential equation would have been equal to R, but because we're going to have some errors because we have an assumed solution, this is our assumed solution that we're going to be using. Those come together to give us our error equation. And so overall we have our error equation, but then we substituted for our second derivative of y with respect to x using our assumed solution. So that's what we have there in parentheses. All right, so now we're going to take that with the subdomain method. We're going to do the integral of the residual equation. It's forced to be 0 for as many subintervals in subdomain as there are unknown coefficients. And again, we only have the one unknown coefficient, just a. We don't know what a is. So we're going to interval over one subinterval. So we're going to go from 0 to L, and we're going to integrate our residual function over that interval. So we go from 0 to L, and we're going to substitute in our whole residual equation that we had from the previous slide and we developed in the first presentation. And we're going to integrate that respect to x and say that all is equal to 0. We're forcing it to say the error to be 0. All right, so we've done the integration. AI pi over L cosine pi x over L minus the moment times x. All right, so we carry through with our distribution of 0 and L, and we solve for A, and we have the moment times length squared minus 2 pi E times the moment of inertia. So if we substitute what we found for our unknown coefficient, we substitute that back in to our deflection equation, we come up with this form. So this is the deflection equation due to the subdomain method being applied to our residual equation. Now, if we would have had two unknown coefficients, right, so not just A, but we also had B, we would have had two intervals where we'd gone from 0 to L over 2, and then from L over 2 to L. All right, we had the two separate equations, and then we could solve. We have two equations we can solve for unknowns, solve for both A and B. All right, so I think there's a homework example has the two unknown coefficients. So just be ready for that when you get there. So that's the subdomain method. Again, go to example 2, which is going to be after all these videos, and you'll see I'm going to use a different assumed solution, and you can see how that works out.